group members.
Hi, my name is Jana Sofia Binti Ibrahimi and my matric number is TE230049. Now I will present about manual calculation using Langrange interpolation. Okay, so we are working on a dataset with a 4-point relating resistance to temperature. Our specific goal is to find the temperature when the resistance is 900 ohm. Since 900 falls between our known data points, we will compare three different levels of precision, which is linear, quadratic, and cubic approximation. Okay, first, we look at the linear approximation. For this, we select 2 points close to our target value of 900. These are 66.0 ohm and 911.3 ohm. Okay, by using first order Langrange formula, by substituting our value, we'll calculate the wedge's influence of each temperature point. The result gives a temperature of 30.5410 degrees Celsius. Okay, this is a straight line estimate, which is a good starting point, but it doesn't count for the curvature of the data. Next, we increase our precision using quadratic approximation. Okay, this time we use 3 data points to form a second degree polynomial. Okay, so this allows the model to capture a parabolic curve through the data. After applying the quadratic Langrange formula and calculating the 3 basis polynomial, we get a combined value of 30.4779 degrees Celsius. Okay, so you will notice this is a slightly lower than our linear estimate. By including more data points, we are starting to see more refined curve fit for the resistance temperature relationship. Okay, finally, we perform a cubic approximation. Okay, in this step, we use all 4 available data points from our table. The formula expands to include 4 basis polynomial, which is L0 through L3. As you can see in the calculation, we sum the contribution of all points, resulting in a final estimate temperature of 30.4618 degrees Celsius. Okay, so as the degree of our polynomial increases, the approximation becomes more stable and better reflects the non-linear nature of the thermistor or resistance data. For resistance of 900 ohm, our most accurate estimate is 30.4618 degrees Celsius. Okay, that's all from me. Thank you.
Hello, my name is Raina Shafika, matrix number AE240093, and today I will present to you the software simulation for Langrange interpolation. The software I'll be using here is MATLAB. First, I'll clear the workspace and the command window to ensure there are no previous variables affecting the results. Here, I input the calibration data provided. R represents the resistance value in ohms, and T represents the corresponding temperatures in degrees Celsius. This is the resistance value where the temperature is unknown, and this is what we want to estimate using interpolation. In this case, it will be 900 ohms represented by RQ. So for this simulation, I'll be using the general Langrange interpolation function that can work with all 3 types of approximation. The input X here is the value where we want to estimate the output. Here it will be RQ. Xn are the known X values, either linear, X value data, quadratic, and cubic, whereas Yn are the corresponding known Y values of the same linear, quadratic, or cubic, and represent the number of data points provided. This automatically determines the order of interpolation, 2 for linear, 3 for quadratic, and 4 for cubic. Number of data points determines how many helper contributions must be constructed. For Y, I initialize Y to 0 because the interpolation result is built by adding contributions from each data point. Now let's go to the outer loop. This is the outer loop. It handles one data point at one time. The variable L here represents a helper value that isolates the influence of one data point. L is initialized to 1 because I am about to build a product, so you cannot have a 0 because if product with a 0, it will become a 0. This is the inner loop. This inner loop performs the product operation of the Langrange basis formula. It builds the helper contribution for the data point. The condition that is being highlighted here ensures that the current data point is excluded, matching the mathematical definition. This is because when j equals to I, the denominator would become 0, and mathematically we do not include that term. Therefore, this condition ensures only the other points are considered. Now that the helper value L is ready, it is multiplied by its corresponding temperature value and added to the final result, forming the interpolation polynomial. Therefore, this completes the general Langrange interpolation function. Now I will show you how the general Langrange interpolation function works by showing you an example for linear approximation. For linear approximation, I selected 2 points nearest to RQ. In this case, it's this one and this one, and also the corresponding this one and this one. So for the R value that I took, I named them as RLin for linear, and that is our xn values. And for the T, I named them as TLin for linear as well, and that is our corresponding yn values. Here I am calling the same general Langrange interpolation function, but with the two given data points. In this case, the x becomes the RQ, xn is the RLin, and yn is the TLin. Finally, I use fprintf to display the calculated result with the 4 decimal places in the MATLAB command window. For both quadratic approximation and cubic approximation, the same steps are repeated. No changes are made to the function itself. It is the same function with only the input data size changes. Like as you can see here, quadratic has 3 data points taken from the nearest to RQ, and for cubic approximation, 4 points were taken that are nearest to RQ. And finally, click run and you will get all the calculated results shown in the command window. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Ni Ikmal Hakimi bin ABDUL, method number CE240227. Okay, now let's look at method number 2 for manual calculation. We using Newton divided different interpolation. Our goal is to estimate the temperature of the system based on its resistance. We have 4 known data points relating resistance R in omega to temperature Fx in degrees Celsius. And we want to find the temperature when the resistance is exactly 900 ohm. Because we have 4 points, we can construct the third order interpolating polynomial. To build the polynomial, we first calculate the divide difference. Okay, first divide difference is represent the slope between adjacent point. For example, f0 power of 1 is calculated as 30.131 minus 25.113 over 911.3 minus 1101, giving us minus 0.0264. We repeat this for the order interval to get minus 0.0363 and minus 0.0541. And next is second divided difference. Here we look at the rate of the change between our first difference. This gives us the value 49 over 2.325 million and 69 over 2.301 million. Okay, the third divide difference, finally we calculate the last coefficient by finding the difference between our second order value. This results in a very small constant that we get is minus 2.02 minus 2.70x7 times 10 power of negative x. Now we use this coefficient to form our interpolating polynomial P3x. We take the top value from each column of our table and plug them into this general form. We estimate the value of x is 900. We estimate the value at x equal to 900 by substituting 900 into our equation. The calculation breakdown into 4 parts. The base value is 25.113, and next the first order adjustment 5.3295, and second order adjustment is 0.0479, and third order adjustment is minus 0.0162. And summing this up, we get a final result of 30.4712. In conclusion, using Newton divided difference method, we can estimate that when the resistance is 900 ohm, the temperature is approximately 30.4712 degrees Celsius.
Hello, my name is Nur Alia Maisara, matrix number CE250051. In this video, I will explain how Newton divided difference interpolation is used to estimate the temperature of a thermistor when the resistance value is not directly available in the calibration data. First, you were given calibration data for an NTC thermistor. The resistance values in ohms are 1101, 911.3636, and 451.1, with corresponding temperatures of 25.113, 30.131, 40.120, and 50.128 degrees Celsius. Our objective is to estimate the temperature when the resistance is 900 ohms. The first step is constructing the divided difference table, where the first column contains the temperature values. Higher order divided differences are then calculated using the Newton divided difference formula. So n length r, this line determines the number of data points, which is 4 in this case. The value of n is used later to control loops and matrix size. So dd zeros and n, this creates an n times n matrix filled with zeros. This matrix will store the divided difference table. This line fills the first column of the divided difference table with the temperature values. For this line, for j equal to n until n, this section calculates the higher order divided differences. The outer loop j moves across columns representing increasing order of divided differences. The inner loop j moves down the rows, and the formula used is the standard Newton divided difference formula. Each new divided difference is calculated using values from the previous column and the difference between resistance values. Moving on, this divided difference table and this dd. These lines display the completed divided difference table in the MATLAB command window, so we can all see computed coefficients. Percent evaluate at R900, x equal 900. This line defines the resistance values at which we want to estimate the temperature. Result dd 1 to 1. This initiates the interpolation result with the first coefficient, which is the first temperature value. For j equal 1 ratio to n negative 1 until n, this loop evaluates the Newton interpolation polynomial. So each iteration updates the product term. The corresponding divided difference coefficient is multiplied and added to the result. This builds the polynomial step by step. Printf estimated temperature at R900 ohm equal to %.4f, which is round off by 4 decimal points and Celsius. This line prints the final estimated temperature at 900 ohms with 4 decimal places for accuracy. So now we just run As you can see, the divided difference table is shown right here, and the estimated temperature at R900 ohm is 30.4617 Celsius. Thank you for watching.
Calculation for this project, we aim to estimate the temperature of a thermistor when its resistance is 900 ohm. To ensure the accuracy, we apply two distinct cubic interpolation method. First method is Langrange interpolation and Newton divided difference using 4 data points from our dataset. We first perform this calculation manually. As you can see on the slide, there was a slight variance between two manual results. The difference in the manual Newton calculation about 0.01 degrees Celsius stem from the cumulative effect of rounding very small value during the second and third divide difference stage. When we move the calculation into MATLAB to minimize the human error, both methods yield the exact same result of 30.4617 degrees Celsius. This consistency proves a fundamental mathematical principle. Both methods generate the same unique interpolation polynomial for a given set of points. For high precision engineering application, we conclude that while both methods are theoretically identical, software-based computation is necessary to avoid the misleading effect of manual rounding.